all the testing methods what we see hereafter are the direct testings. Hence, we need to consider or we need to look into a, a different losses, whatever the losses we calculated. In the load test, we did not calculate losses because directly we could obtain the efficiency from the input and output relations. In OCA test or in the no load test, Swinburne's test, we calculated constant losses, which we assume that they remain practically constant throughout the operation. But even though we can estimate the efficiency in Swinburne's test, but we cannot exactly know what are the losses that will occur when the machine is loaded, when the motor is loaded. So when the motor is loaded, the losses which we already have seen are not the only losses which exist. Okay. Few more amount of losses will come into picture. What are those losses we will look into first briefly. Then we'll move into the next step of or the next type of testing method for a DC machine. Okay. So next what we look into is spray losses. As the name suggests, these losses are stray. Stray means they will exist anywhere in the machine. Okay. So what are these losses and what changes we see in the losses when we load the machine or when we load the motor? Okay. So here, give me a second. Am I audible? Am I audible? Am I audible?
Yes, sir, but very less voice.
Now, am I audible? Hello?
Sir, volume is very less.
Is my voice clear?
We can't hear.
No? Now, am I audible? Now, am I audible?
Yes.
Sir.
Yes.
Okay. So now, when the motor is loaded, when the load current is flowing in the armature conductors, then the behavior of the motor and its losses will change. What we have approximated in the test currently is that the losses will remain constant, so we did not worry much about what happens at the load condition. But now, when the motor is loaded, now almost every test what we see now is the load test, okay, where we are loading the motor in one or the other way. In such cases, when the armature, considerable amount of armature current starts flowing, then the behavior of the motor changes. The temperature rise changes, the flux linking changes, and moreover, we get armature reaction effect. Okay, when the armature current was very low, the effect of armature reaction was negligible. At no load, the effect of armature reaction is negligible. But I cannot neglect the effect of armature reaction when the considerable amount of armature current is flowing in the circuit or in the motor. Now, when you see the motor, this is a DC motor, okay, a cut section of DC motor. These are the poles. Okay. This is armature. Okay. Here we have commutators. Okay. These are brush holders. Okay. So we have brushes here. These are brushes. This is the cover or yoke. This is shaft. Okay. These are field coils. Okay. These are armature conductors. Okay. Here we have bearings. This is fan. These are end plates. Okay. Lot many other fixations are there. Rivets are there. Nuts and bolts are there. Okay. Screws are there. These are the parts of a DC motor or any motor. Now, when this conductor starts carrying current, when the conductor starts carrying current in the armature, it will create its own flux. Okay, this armature conductor will create its own flux phi A. Now this flux phi A will start reacting upon the main flux phi. So this is the main flux phi produced by the field. Now there will be a continuous interaction between phi A and phi, and as a result of that, there will be the effect armature reaction. And the effect of armature reaction are two. One is demagnetizing effect, and the total flux produced by the main field will decrease. The second is cross magnetizing effect, which will distort the uniform distribution of the main flux, which is now the reason for my stylosis. Okay. No doubt the flux is decreased. I can increase it by adding few more number of turns in the field coils. That can be done. But how do we come across or overcome the cross magnetizing effect? We use interpoles and compensating winding, which will reduce the cross magnetizing effect. That is fine. But I cannot eliminate it completely. So here, as a result of cross magnetizing effect, what will happen? Or as a result of field distortion, what will happen? The main flux wave will not be a uniformly distributed flux wave. Now, if you observe the flux wave, okay, now let us consider a north pole and south pole. Suppose this is north pole. This is south pole. I will take side by side rather than in the circular path, so that I can plot a wave. So this is MNA, magnetic neutral axis. This is MNA. Okay. So there is a south pole before north pole. There is a north pole after south pole because we are placing it in circle in revolution. This is MNA. If you observe the field wave, flux wave, if it starts from MNA, okay, it will increase. Suppose this is the reference axis, or with respect to time, or we'll take with respect to theta, angular position. That is good. At MNA, the flux is 0, flux or flux density, B, let it be. Okay, flux or flux density. So at M and a magnetic neutral axis, my flux is zero. When the space falls under the pole, the flux starts increasing. And observe, from almost the edge of the poles, or almost the edge of the poles, the pole phase is constant. So the area P is constant. You can observe. So let this be the armature. Sorry, let this be the armature. And if you see the pole structure, it will be like this. So at the tips, the area P is a little bit more. At the center, the area P is a little bit is minimum. So here the air gap is more, so therefore the reluctance is more. Here the air gap is more, reluctance is more. After some time, from almost this point to this point, air gap is almost constant. Therefore, the flux will remain constant, as the reluctance will remain constant. So the flux will remain constant like this. Again, it will decrease to 0 on MNA. Negative direction, the flux will increase in this direction. So generally in almost all the machines, the flux is a flat topped waveform. It is not a sinusoidal waveform. Most of the times, the flux is flat topped waveform. It is not a sinusoidal waveform. If this is the case, then we call this as the constant flux density wave, okay, or undistorted flux density wave. Now, after armature reaction, when the armature flux reacts with the main flux and it will distort, it will be the wave. So as a result of this distorted waveform, this is called harmonically affected wave. You heard of harmonics?
Yes,
Yes.
sir.
Where did you hear of harmonics? Where did you come through across harmonics?
In AEC also.
In AAC. In which part? Power amplifiers.
Yes, sir.
Yes, there you calculated total harmonic distortion of class B amplifier. Yes. What is
Yes,
harmonic?
sir.
What is harmonic? And even in transformers, there is one topic. Effects of harmonics on transformer. Yeah. What is harmonic? First, being electrical engineers, you should be knowing what is harmonics by default. From the very earlier part of your study only, you should know. This already you have studied this in 2 subjects.
Sir, it is distortion.
It is not only the distortion. You should be telling technically what is harmonics, because that understanding we need to understand stray losses here.
Presence of frequency components in the output waveform.
Yeah, presence of frequency components in the waveform. Okay, so lower frequency components or higher frequency components. Yes, presence of
Lower
lower frequency components or higher frequency components.
lower frequencies.
If there are lower frequency components, then I should not worry, because losses will be reduced. So when I'm talking about the losses because of harmonics, means it should be higher frequency components. So harmonics, I think this I have explained even in ECA once in one of the class. I think especially in resonance. I remember. Okay, fine. Okay, so harmonics are the integral multiples of fundamental frequencies which are superimposed on the fundamental wave. So fundamental wave is this one. This is called fundamental wave. This is called harmonically affected wave. Okay. So harmonics are the integral multiples of fundamental frequencies. If you say take a sine wave, this is the problem when you forget everything. Every time we have to invest our time and energies to go back and tell the same thing. Hmm. So this is fundamental frequency. If I take a third harmonic, because second harmonic doesn't exist for sine wave. This is a third harmonic, which is having frequency thrice the fundamental. Thrice means in one cycle of fundamental, there are three cycles of harmonic wave. Then next, if you take fifth harmonic, this is fifth harmonic. As the order of harmonics increases, the amplitude of harmonic wave decreases. If you take seventh harmonic, the amplitude will be still smaller. Ninth, 11th, 13th harmonic are generally discarded because the amplitudes are so small that they can be neglected. Only third, fifth, and seventh are taken into account. Now, when these two harmonic waves get superimposed on the fundamental or they get added to the fundamental, what will happen? The fundamental wave may not be a sinusoidal wave. Am I audible?
Yes, sir.
Yeah, because there is a continuous power cut here. I don't know. So it is good now. But it is not expected from our side. We should somehow get connected with you. Now, this is the resultant waveform. This is called harmonically affected wave. Harmonically affected wave. Now, the same thing happens with flux wave in the DC motor when the armature conductor starts flowing. Now, because the DC motor flux wave is not uniform, the EMF induced in the armature conductors is not sinusoidal. Therefore, the current flowing in the armature conductor is non-sinusoidal. That is, the current produced is harmonically affected. So, because of which, the iron losses in the machine increases. So, this is F, this is 3F, this is 5F. And we know iron losses are directly proportional to the frequencies. Now there is iron loss in a core because of one frequency, because of three frequency, because of fifth frequency. So these two components, okay, harmonic waveforms are increasing the iron losses in the machine. These are increasing the iron losses in the machine. Okay. And these iron losses cannot be found out so easily. Because at what point of time, what harmonic content is effectively operating, nobody knows. This is one case of stray losses. That stray losses occur because of the distortion occurred in the main field flux because of armature reaction. Second, because of this distorted flux wave, the EMF induced in the armature is non-uniform. The current induced in the armature conductors is non-uniform. As a result of that, there is non-uniform leakage flux present in the armature area or motor area. This non-uniform flux produced in the air gap will induce non-uniform EMFs in the conductor again, okay, which will also circulate the current again in the conductor. Apart from load current in the armature conductors, there is a leakage current in the armature conductors which is flowing because of leakage flux, and this current is known as conductor eddy current. So eddy currents are not only flowing in the iron part, eddy currents are flowing in the conductor part also. So there are conductor eddy currents also. Why eddy currents are flowing in conductor? It is because of the leakage flux created by the conductor. Okay, what do you mean by leakage flux? What is leakage flux? Anybody? Yes. What is leakage flux? Divin Kumar, can you tell what is leakage flux?
Sir, it is because of the uh, no, sir, I don't know properly.
Gayatri?
Yes, sir.
Yeah. What is leakage flux?
Sir, leakage, magnetic flux, sir, which doesn't it doesn't flow particularly in the path of the circuit, sir.
Okay. Yeah, to some extent it is fine. Okay. So as a result of this, what will happen? Because of presence of leakage flux in the armature conductor. Now observe carefully what leakage flux in the conductors mean. This is the field which is creating the main flux, right? Okay. This is the armature. I will take only one conductor. This is the armature conductor which is carrying current and creating flux. Okay. Now, distortion of the main field flux occur when the armature flux created interact with the main field flux here. And some part of the flux created by this armature conductor may not link the main field flux. It will complete its path around the conductor only. Okay. So that flux which is creating, which is a leakage flux which is completing its own path around the conductor, is linking this conductor again. And please remember, okay, the current flowing in the armature conductor is AC, alternating. Therefore, the EMF is induced in this conductor. The flux created by the conductor is linking the same conductor. Therefore, EMF is induced in the conductor. It is not back EMF. Please remember this. Black EMF is created because of the cutting of the main flux by the conductor. Back EMF is created because of cutting of the flux, main flux by the conductor. Now, there is a EMF induced in the conductor because of the linking of its own flux to the conductor. That is called eddy EMF, which will circulate the current in the conductors, which is called eddy current. So this is known as conductor eddy current. So there are eddy currents or circulating currents even in the conductor part, not only in the iron part. So these conductor eddy currents also are effectively increasing the resistance of the conductor because they are causing the losses, eddy current losses in the conductor, because of which the total losses in the machine increase. This is one kind of loss because of field distortion. Okay. Now, because of field distortion, the flux which was supposed to be a uniform, which is non-uniform. Okay. So we have this conductor. This is a teeth part. Okay. This is armature. This is slot where conductors are kept. This is teeth. Now this teeth, which is iron part, subjected to this non-uniform flux wave, there will be EMF induced in this teeth, which is non-uniform. Currents produced in this teeth, which is non-uniform. There will be losses, additional eddy current losses in the teeth. These are also the part of stray losses, and these all type of losses will occur only when the armature conductors start carrying current, that is under load condition. Okay, so there are additional losses in the teeth, there are additional losses, eddy current losses in the conductor, there are additional iron losses in the core because flux is non-uniform. These frequency components 3f square, it means my hysteresis loss is proportional to 3 into Bm raised to 4.5.2. It was 3.6, right? So 7.2, not 5.2 into 2, 7.2. Eddy current losses are proportional to 9f square. 9 times the eddy current losses are increasing. Here it will be 25f square. Okay. And Bm hysteresis loss is proportional to 5 into Bm raised to 10. 3.6 into 5, sorry, not Bm raised to 10. Some larger power, not 7.2, more than that. Okay, f square, na? So 5 into Bm raised to 7.2. So iron losses in the core is increasing because of harmonics. That is the reason why everybody is worried about harmonic content present in the current wave. We should never allow harmonic content present in this current wave. It should always be kept in a very, very, very low or no harmonic content condition only, because they will increase iron losses in the entire system to a very large extent. Though they are in less in magnitude, but their frequency components are more. They are quite prominent. Okay, so these will form the additional losses in the machine, which are the part of stray losses. Other losses that will occur. Now, the armature flux created will link to bearing. There is an circulating current in bearing. Will link to shaft. There is circulating current in shaft. Will link to brushes, brush holders. There are circulating current in brush holders. It may link to outer cover, end plates. Every iron part is a magnetic part where the EMFs can be induced and circulating currents can be produced. And these stray losses are not individually measurable losses. That is the biggest difficulty of stray loss. Okay, that is the reason why it is not stray loss. Because we don't know in which all parts the losses are existing. Okay, it may happen that in one bearing there may be stray loss, in other bearing there may not be stray loss, or there may not be losses. One end plate may be incurring losses, other end plate may not be incurring losses because there may be no circulating currents in that. So these stray losses are the losses which will include all the losses present in the machine, in all the parts, which will also include copper losses in armature. Okay, total loss. If I consider total losses, copper losses in armature, copper losses in field, iron losses in core parts, plus stray losses. These are the actual losses when the motor is an operating condition. But As a whole, I can find out stray losses through some analytical techniques, but in particular, it is very difficult to find what are the losses in each part of the machine. Hence, those losses are known as stray losses. Those cannot be easily measurable. Those are not easily measurable. Okay. So this is a very brief introduction to stray losses, because hereafter in all the testing techniques, we calculate stray losses. Whether a shunt motor or series motor, we find stray losses hereafter. Okay. So is it clear what stray losses are? Stray losses mainly occur due to the distortion of main field. Stray losses mainly occur due to distortion of main field. If distortion of main field doesn't occur, then stray losses will be very, very minimum when compared to the distorted field. Okay. So whether there is a distorted field or not a distorted field, there will be small amount of iron losses present always in the shaft, bearing and brush holders, because they are directly in contact with armature. So the fluxes acting will definitely create some losses. Okay. So for that, what we can do is we can increase the length of the machine. If I increase the length of the machine, okay, here if I keep the what we can say bearings little bit away from the active armature area, then the reluctance between the armature and the bearings will increase, and probably the flux linkage may not happen, and the circulating currents can be minimized. But if I do that, the material required will increase, machine become bigger, more cost will be incurred. Okay, so that is a design problem. Okay, so when you study design, you will come across many of such things in the machines. Okay, where your hands will be tied. You have to compromise. Okay, so is it clear about the stray losses?
Yes, sir.
Yeah. So next we'll move to the next type of test, which is known as Hopkinson's test. Hopkinson's test. This is also known as regenerative test. Also known as back-to-back test. Okay. So before giving introduction to this test, first I will draw the circuit diagram. When I saw the circuit diagram, and when I draw the circuit diagram and you see it, most of the things will be observed, whatever I will be explaining, or else I will be simply explaining without circuit diagram. You people have to imagine many things if you listen. Okay. So first I will draw the circuit diagram. A DC motor is coupled to a DC generator. So here in this test, we are using two identical DC machines. Both should be identical. Rating should be same, voltage value should be same, current rating should be same, rated speed should be same, everything should be same. So these are not only mechanically coupled, these are also electrically connected. Both are shunt machines, and this test is also carried out on either shunt motor or compound motor, or shunt and compound machines, we can say in general, because both generator and motor are involved. So we can say like that. This is the connection. Okay, what are the currents and all later we will look into. So first we will see the connection. So what we are doing here? Okay, so what we are doing here is we are taking two identical DC machines. One I will operate it as motor, other I will operate it as generator. How it will happen? Because both motor and generator are connected in parallel to the supply. If I close the switch, and give the supply voltage V, then both the machines start operating as motor only, because both are given with field supply as well as armature supply. And mechanically coupled motors will run at the same speeds. So my need is not satisfied here. I want one to operate as motor, one to operate as generator. Okay. So what I do, I will mechanically couple two electrical identical machines. Then I will vary the field system. I will vary the field winding. Okay. One machine act as motor. Okay. This is done by weakening the field. This is done by weakening the field, keeping the switch as open. Okay. So first thing, what we have to do is keep switch open. Now, when I keep the switch as open, there is no electrical supply given to the generator. Okay. Then one machine acts as motor. The machine whose field is weakened, it means that I go on increasing the rheostatic value. That machine will act as motor. Then one machine act as generator. Okay. This is done by strengthening the field. By strengthening the field. It means that here for a motor, I am decreasing the field current. For a generator, I am increasing the field current. That's it. Weakening field means decrease the field current. Strengthen the field means increase the field current. So how do I do that? Initially keep the motor field rheostat to 0 and generator field rheostat to maximum. Then later, when you give the supply voltage V, keeping the switches open, increase the motor field rheostat and decrease the field current. Later, decrease the generator field rheostat, increase the field current. Okay. So with this operation, I can make one motor or one machine to be operated as motor, other machine to be operated as generator. Okay. So the machines are so connected that when they start producing their outputs, now the moment I make this machine 1, let me take for reference machine 1, machine 2, initially to recognize. When I make machine 1 to operate as motor, it start giving out the mechanical output, which is connected to the generator. Generator will start getting mechanical input. So machines 2 starts operating as generator and start giving out electrical output. Now when I close the switch, mechanical output of motor is given as input to generator. Electrical output of generator is given back as input to motor. Then what is the use of this supply? We will come to that point. Now the output of motor is given to generator. The output of generator is given back to motor. So because the outputs are connected back to back. This is called back-to-back test. Okay. Motor is taking input from generator. It is producing the output, giving to motor, giving to generator. Now generator is taking the input from motor. It is producing the output, giving to motor. So there is a back-to-back transfer of power, back-to-back conversion of power from electrical to mechanical, mechanical to electrical in the same system. Hence, this type of connection or this type of testing is known as back-to-back test. Okay. Then what is regenerative test? Why it is called regenerative test? As the output of each machine is fed as input to other machine and they are producing their outputs again, the output is regenerated. The input is regenerated, output is regenerated. So the power is regenerated in this loop. Hence it is called regenerative test. Whatever the power is generated by the generator, it is fed to motor. Now motor is giving that power back to generator to generate the same output. So the power of the generator is regenerated in the same system by using the same output. Hence it is called regenerative test. Clear? Yes. Are the things clear?
Yes, sir.
Okay. Now how it is full load test? This is also full load test. This is a direct test. Now when the system, don't worry that this is the final explanation. This is only the how the system is operating. Step by step, how to take the tests, we will again look into. This is to understand the definition of the test and the operation of the test. That's it. Okay. This is an introduction to the Hopkinson's test. Now it is also a direct test or load test. Why it is called direct test or load test? Because motor is acting like load on generator. Generator is acting like load on motor. Is it? Electrical output of generator is given to motor. It means motor is load on generator. Mechanical output of motor is given to generator. It means generator is load on motor. Hence, both the machines are loaded. It is a direct test. Okay. Now, what is the function of supply voltage or supply terminals when there is a back-to-back generation of or there is a regeneration of the power? Once after the first cycle or first excitation of motor and generator, okay, the supply can be taken out if and only if both the machines don't have losses. But we know practically DC machines are having losses. Okay. Now suppose I once excite the machine and I take out the supply. Will this system run forever? Or no? I will excite the machines for the only first time, only once from the external source. Then I will take out the supply out. Will this motor generator set with regenerative mechanism operate forever? Or no? Yeah, first quickly.
No, sir.
Will there be regeneration of power forever or it will stop after some time?
It will stop.
It will stop because there are losses. See, for example, machine is 90% efficient. Say motor is 90% efficient. Generator is also say 90% efficient. Okay. Now first I am making motor to operate before generator starts operating. Suppose I am giving 100 watts of power to motor. What is the output? 90 watts. Is it? 90% efficiency means 90 watts only, now out of 100. Now, generator is getting 90 watts power. How much it is giving? 81 watts. If I consider the linear relationship. Right? Now, motor how much is getting? Suppose
81.
after providing first 100 watts, after providing first 100 watts, I once the motor starts operating and I connect a generator in parallel to motor, I will take out the supply. Now supply is not there. Only the electrical output of generator is given to motor, mechanical output of motor is given to generator. Now, when 100 watt was received by the motor, 90 watt was the output. Now it is receiving 81 watts. What will be the output? Yes. 90% of that, how much? You use
72.9.
72.9 watts. Now, how much generator is receiving output? 72.9 watts. How much it will give? Less than 90%. 65.61. So, after every cycle of regeneration of power, the power is reducing by how many percent? Power is reduced by how much percent?
10%.
20% after one cycle. Why? Because 10% loss in motor, 10% loss in generator. Yes? Yes or no?
Yes, sir.
So, within few seconds, motor and generator both will stop operating. Then what is the function of supply? Supply voltage or supply terminal? See, whatever the power required by the motor to generate the output is given by the generator. Whatever the power required by the generator to generate the output is given by the motor. Then who will supply the losses? The losses are supplied by the external power supply. So the biggest advantage of Hopkinson's test is that for the testing purpose, though it is direct test or load test, entire power of two machines is not received by the supply terminals. Only the losses, to satisfy the losses in both the machines, only that much amount of power is received by the supply terminals. So the power required to develop the outputs in each machine is given by the other machine. So whatever the amount of power, so 90% efficiency generator I have na. Okay, suppose both are of 100 watts. This also 100 watt, this also 100 watt. Identical machines I told. So 90 watts is provided by the motor in the form of mechanical input. 10 watts is received by the supply. 90 watts is provided by the generator for the motor. 10 watts is received by the supply. Okay. So how much power is drawn from the supply? It is 20 watts. 10 watts of loss in motor, 10 watts of loss in generator. Suppose if both the machines were directly loaded using the same supply, how much input power was required to test? 200 watts. 100 watt for this machine, 100 watt for this machine to conduct the load test. Right? So Hopkinson's test is one of the advantageous method of testing DC machines, where though it is load test, but not all the power required to conduct the test is drawn from the supply, but only the amount of loss power is drawn from the supply. But the disadvantage is that I need two identical machines. So capital investment is more here. That is one case. Okay. So this is the brief introduction to Hopkinson's test, exact operation and methodology, and how to get the equations of efficiency and losses, and what are stray losses already we have seen. Okay. Those all things we will look into the next class. Okay. So tomorrow I have class. In the tomorrow's class, we will look into the exact operation of Hopkinson test. Okay. Tomorrow I will be taking 2 lectures, 2 hours. Second hour I have regular. Third hour, instead of PGE, you will be having motors class. Okay. So instead of power generation class tomorrow, you will be having electric motors class. Which class you have next?
EMFT.
Field theory.
Yes, sir.